Okay, we got a somewhat complicated problem here, not, but it's going to fall apart. Just starting out a little complicated. My screen fixed here. All right, this is statistics. Many fire stations handle more emergency calls for medical help than for fires. At one fire station, 81% of incoming calls are for medical help. Suppose we choose 4 random calls to the station. Well, that explains it, at random. Uh, find the probability that all 4 calls are for medical help. And we're going to solve all these other problems here. So uh, this is something that if you didn't know, this falls under the area of the binomial probability distributions. So let's give it a name. So this is an area called the binomial probability distributions. Big words, confusing, yes. And it relates to discrete random. And if you wanted to know where this fits in, it relates to discrete random variables. Okay, and so basically there's a few types of distributions that deal with discrete random variables, and this is one of 3. So this is a good one we all like to teachers will like to cover. There's another one called Poisson, Poisson, and the third one would be called hypergeometric probability distributions. So hypergeometric probability distributions. Okay, so you have all 3 of these deal with discrete random variables, and one of the most elementary and useful and interesting ones is the binomial probability distribution. So we're going to do so what people relate this to, which makes it become easy for us, is it's like a coin toss, okay, in that if you said, well, I want to have so many heads, and if you said, well, a head is getting ahead is a success, okay, and then getting a tail would be a failure, okay, and then the probability of getting ahead each time you toss it would be 0.5, okay. So there's your success probability, and you have the other way would be a failure. Now, I understand that in a trial, one trial would be tossing the coin one time. Okay, one toss. Okay, is one trial. All right. Now, if you did this, you would say, what's the probability of you getting ahead? Well, it's 50%. But now, if you do this again, the probability of success doesn't change. So on the second trial, okay, the probability of success remains unchanged. Okay, so it still is probability 0.5. Okay, so you still have the probability of 0.5. And the previous trial did not affect the second trial. So we call this trial independence. So the trials are independent of one another. Okay, so this is an important aspect of this kind of problem. Okay, and then you're getting and then the probabilities are staying the same. That's also an important aspect of this problem. The probability of success is remaining unchanged. Okay, so that's an important aspect here of this problem. Okay, um, let's see. We're going to call this, when we get this kind of situation, we refer to it as a binomial setting. Okay, so if we have a binomial setting in a problem, then we can use this binomial approach. Okay, so that's what we can use this. Now, what is this binomial setting? All right, what is this binomial setting? Okay, what does it have to include? Okay, um, it's the same. Okay, every trial, okay, is the same. All right, so and it's random. Okay, it's random. All right, every trial is the same. Chance process. All right, and we will record the number of successes, say. All right, and we're going to do several trials. Okay, for several trials, and so we're going to say, well, we're going to do this thing, and then at the end, we're going to say, well, what is the probability of 3 heads, right, out of 5 tosses? Okay, see, so that's where we're coming to something like this. We want to know the probability of 3 heads out of 5 tosses. So really, this is saying the probability of 3 successes out of 5 trials. Okay, so that's another way. Now, let's make this concrete even more. So we refer to something as binary. Okay, binary, which means the outcome is either a success or a failure. Okay, now you don't have to have coins. You can have a bag full of marbles. Okay, and each of the marbles are different colors. All right, and here's the catch. So when you take one of the marbles out, you say success is a red marble. Okay, and that's great. But if you got a green one, or a blue one, or an orange one, or what have you, that's a failure. Okay, so success is getting a red marble. And the thing is here, you can have failure by having not only 2 different ways, just one is success and one is failure. In terms of there's only 2 possible outcomes here. There could be more than 2 possible outcomes, but what we're saying is that the outcome we're interested in, that we call success, is the red marble. The green, the blue, the orange will all be failures. So then you put them all back in, and then every one of them goes back in, and you pick a new one out, okay, at random. Okay, so um, there could be more than 2 possible outcomes per trial, um, but we define success as the red marble, okay, and failure as all the others. So that's why we refer to this as a binary kind of in this what we say binomial setting type of problem. We have a binary kind of situation. It's either a success or a failure. That's it. Okay, independent. All right, independent means that the trials are independent. Okay, the trials must be independent. Uh, the outcome of one trial has no effect on the outcome of a subsequent trial. Okay, so what are we saying? That's saying that, all right, when you toss the coin, you got a head and a tail is a failure. Well, you got a success in the first toss. But when you toss it again, you have the same probability of getting a head. Okay? It's like if you're choosing these marbles, you put the marbles back in, and now you have the same chance of getting a red marble as the first time. So it's not like you're taking the marble out and keeping it out. Now you've altered the amount of red marbles that are in here. That would not be independent. And the last thing here, uh, well, second to last, is the number. The number of trials. The number of trials. Okay, which we refer to as n, little n, of the chance process must be fixed in advance. So the number of trials you're going to have has to be fixed in advance, okay? You just can't go on and on and on. You have to have a certain number of trials, okay? And success, as I said, on each trial, the probability of the success is the same. The same for all trials. Okay, so let's go over that. We can use the binomial probability distribution when we have a binomial setting in a problem. And that refers to something that we'd like to say the outcome is either a success or a failure. Okay, and you could define success how you like and failure how you like, as long as the trials are independent. That no future trial is affected by a previous trial, and the number of trials is fixed in advance, and the probability of success for all trials remains the same. And there is one more small thing here, and that is for this to be binomial, we have one more condition, and that is that the number of trials over the total number of in the population. Okay, these are the number of trials. This ratio, as a rule of thumb, um, has to be less than or equal to 0.05. This is a condition. So if it's great, if you have the number of trials is over the number of population is greater than or equal, it has to be less than 0.5, because then greater than or equal to 0.05, then this will not be a binomial setting. Okay? So you have to have this. Can't have that. Okay? All right. Then you deviate from the binomial setting. All right, without going into too much math and figuring out what the binomial theorem is and all that, we're going to try to solve our problem. So again, here's our problem. Find the probability that all 4 calls are for medical help. So we have to identify what we have here. Well, we have that we're going to choose 4 random calls. So n equals 4. Okay? Now the probability of the fire station getting a call for medical help is 81%. So let me just say the probability of medical help call, okay, equals 0.81. All right, so the probability of a fire call, okay, I'll just put medical. Probability of medical is 0.81. Probability of fire would be the 1 minus this number, because that would cover all the probability would be equal to 1. So probability of both of these is equal to 1. So the probability of fire is subtract 1 minus this number. And so 1 minus 0.81, I get 0.19. So there's the probability of a fire call. Now, what are the probability that all 4 calls are for medical help? Okay, so here's where you get into the equation of this thing. It's pretty ugly looking at first, but it's very doable and not too bad.